So we've been looking at reaction rates as a function of the change in molarity over the change in time. And we now know that we can use the coefficients from our balanced equation to allow us to kind of relate, okay, if this thing is decreasing by this factor, how then must my other reactant be just decreasing, or how is that affecting the rate at which I'm creating my products? We can use coefficients, get our rate expressions, which is great. Nice way for us to kind of relate those two together. But there is kind of an easier way. And there's also some other pieces we need to take into account when we start to think about how quickly is our reaction proceeding. And so our kind of next piece of the puzzle is our reaction law, or our rate law, as opposed to our reaction expression. So our rate law is a mathematical equation that lets us express the rate of our reaction as a function of a bunch of different things all at the same time. Reactant concentrations, product concentrations, the temperature. This also is going to inherently incorporate how our molecules are structured, how they must be colliding in order for a reaction to take place, and kind of the factor of temperature and the speed of our particles, all wrapped up into one super handy, user-friendly reaction law, or rate law. And so our rate law is this kind of formula over here. This is the generic form, where we're going to have a constant. K is what's called our rate constant. It's going to be unique to a reaction at a certain temp. It does not change as the reaction progresses. It is a constant throughout the whole rate of the change of the reaction. Here in brackets, we've got our reactants A and our reactant B, and then they're raised to these M and these nths. And these are what are called the reaction or rate orders. This is essentially how important is molecule A in the overall rate of the reaction. How important is B in the rate of the reaction? Because for some reactions, we might change the concentration and it doesn't change the rate of the reaction at all, which means it doesn't actually have any effect on how quickly the reaction proceeds. Our other substances are. And so the rate order here kind of tells us, well, what factor or what effect does this particular species have on the overall rate? Not to be confused with our expressions. We already did reaction expressions. This is what we had in the last video, where we're saying what is the change in concentration per change in time. That's what the coefficients. M and N are not related to the coefficients. They're just what we call our rate orders. And we got to actually figure those out experimentally. We got to actually collect some data to get both of those and that rate constant for the given temperature that we're working at. So couple of examples, or a couple more terminologies here. We're going to have a separate video with, I'm going to work through a whole kind of example problem of how we would find all of these values. But we actually have a way to get all of that. Today, we're just going to look at some of the verbiage, some of the terminology, so that we know how to kind of say these different pieces. So notice here, if this is our overall reaction, we've got substance A reacting with B and C and D. The red letters here are the coefficients. You'll notice they're not in the rate law at all. We do not use the coefficients for the rate law. Those numbers are the rate orders. Those rate orders, we would say, so for example, for substance A, we would say that the overall rate of this reaction, when we incorporate all the reactants and the temperature and how they're colliding, all combined together, we say that it is third order, or directly proportional to the cube of A. We would say it's third order with respect to A. And if it's a 1, or just if it was just B with no power, we would say that's directly proportional to the concentration of B. It is first order with respect to B. If we had kind of the square, if it was a squared value, we'd say that, for example, for C, it's second order with respect to C. And if it did not have an effect at all, if we put in more D, substance D, and the rate didn't change at all, it still took just as long for it to go, we'd say that it's 0th order with respect to D. D didn't have, changing the concentration of D had no effect on the rate at which our reaction progressed. And so if we were going to rewrite this, we can kind of drop the 1, it's implied. We can drop out D entirely, and we'd say, here's our overall rate law. It's proportional to the cube of A times B times the square of C. And then if we want what we say the overall order, we actually just add the exponents. 3 plus an implied 1 plus 2, so 2 and 1 is 3, plus 3 is 6. This is 6th order overall, is how we would kind of go about saying that, describing how our different reactants are affecting the overall rate of the reaction. Another example, just to kind of look at, so for each of the following, determine the reaction order with respect to each reactant and the overall order from the given rate law. So for this first one, we would say it's second order with respect to nitrogen monoxide, and it's first order with respect to the oxygen, and it's third order overall. Here, you try this next one, and then we'll go over it. It's pretty straightforward. It's 3/2 with respect to our CH3CHO, and it's 3/2 overall. Oh, it might not be a whole number. Oh, that's tricky. Again, there's a lot of factors that are all kind of wrapped up in that rate law. Another one for you here. We've got H2O2 times I minus. Oh, this one was actually the catalyzed reaction that we saw in the elephant toothpaste. Huh. We say it's first order with respect to hydrogen peroxide and first order with respect to the iodide ions. And so we got the exponents. It is second order overall. Second order overall. Cool. Just a couple of terminologies to be thinking about as we start to think about our different rate laws. For this one, we would say that with respect to each of our reactants, it's first order with respect to the bromide, first order with respect to the bromate, that's that BrO3 species, and second order with respect to the hydronium or the H+ ion. And so 2 + 1 + 1 is a fourth order overall for this particular example, fourth order overall. Cool. So just some terminology, what these values mean for us. In the next video, we'll dive into how we actually go about calculating these and how we get these numbers. They have to be determined experimentally. We actually got to collect data and work backwards to it. But the good news is math is pretty straightforward. We just need to see some examples of how we go about doing that. Cool. Thanks, guys. I'll see you on the next one.